Okay, next topic. Vector cross product, the vector formalism, which that's what I've been showing in that Excel spreadsheet, setting up an Excel spreadsheet to handle the vector formalism. And we looked at the right-hand rule earlier also. So cross product. If you have coplanar forces in the XY plane, the moment's in the Z direction. If it's in the positive Z direction, it's positive. If it's in the negative Z direction, it's negative. Something tending to turn a system counterclockwise is positive. It goes in the positive Z direction. Counterclockwise rotation is negative because it tends in the negative Z direction. So the magnitude of A cross B is AB sine theta. We saw that way early where we looked at the line of action of the force times the perpendicular distance from, or the shortest distance from the axis to the line of action. That would be the distance times the sine of the angle between the force and the lever arm. D sine theta times the force. That's where we get the sine of theta coming from. Then UC is given by the right-hand rule. It's a unit vector in the C direction. But sometimes we can't tell what that vector is easily. We got to use the full mathematical components, formulas for finding the cross product. And last thing, the result, the C vector, is perpendicular to both A and B. Oops, wrong. Come on. Wake up, Jim. Went too far. Flipping around a bit. Slow electron, slow computer. Okay. It's what's called anti-commutative. A cross B does not equal B cross A. And you just try that with the right-hand rule. Just flip the A and B axis and you'll see that your fingers are flipped around. It's A cross B is negative B cross A. That's what we call anti-commutative. Okay. Scalar multiplication, if you multiply A times A cross B, it's the same as multiplying vector A by the little a, or vector B by little b, or the whole thing by little a. So vectors or scalars times the vectors, just associative, distributive, all that stuff still applies. It distributes. So A cross B plus D equals A cross B plus A cross D. The cross products of I hat, J hat, and K hat. This is a good little table. So I hat cross I hat, 0. I hat cross J hat is K hat. You'll notice we're finding the row I hat, J hat, K hat times the column vector. If we flipped it in reverse, we'd have negative signs everywhere. So I hat cross K hat's negative J hat. J hat cross I hat's negative K hat. J hat is 0. J hat, K hat is I hat. K hat, I hat is J hat. K hat, J hat is negative I hat. And K hat is 0. Ki equals J. Ij equals K. There's the circle. Jk equals I. Positive sign. Going the other way, Jk is negative I. Let's see. Oh, excuse me. Kj is negative I. Kj is negative I. Ji is negative K. Ji is negative K. Ik is negative J. Ik is negative J. That's what this circle represents. Another way to remember the unit vectors times crossed into each other. Then, of course, here's the right-hand rule that I cross J equals K. And you use your hand, your right hand, just point thumb along the I hat. In this case, they're curling from the I to the J, and the thumb is pointing in the resultant vector direction. or thumb along I, index along J, other three fingers or palm point toward K. And you can test that. Just any of the three axes any time. Just grab your right hand, and most of you will have one, and just do it. Component form, when you expand this out, ax times bx, I hat times I hat 0, ax by k hat, where is it? Ax by, ax bz negative j hat, there's ax bz, ay bx negative k hat, there it is, ay by 0 doesn't exist, ay bz is positive I hat, there it is. And then A's, well, anyway, you get the idea. Just do all the distributive stuff. Determinant form, you can do it this way also. So let's go back to the determinant form. Just evaluate the determinants. I hat times this subdeterminant. Remember how determinants work? You have positive, then you have negative. Negative j hat times the ax, bx, az, bz subdeterminant, which would give you negative j hat, ax, bz. There it is. Negative j hat, ax, bz, just like this formula. And negative j hat, negative az, bx, positive az, bx, j hat. And then k hat times this subdeterminant, ax, by, ay, bx. Another way is to think of it is down these diagonals. These will all be positive. K times ax by. And then I hat times az by is going to be negative. K hat ay bx negative. J hat ax bz negative. A couple ways to do determinants. Okay. Moment about point O, R cross F. And we've been talking about that. Radius times lever arm. Here's the sign of the angle. You can visualize R as being the point of the origin, that R can, the tail of the R vector can be on the line of action of the force, which might make it easier for you guys to visualize these vectors. Okay. R can be any vector from point O to the line of action of the force. Because let's say you have R1, R2 plus delta R equals R1, and if you just make that substitution, R2 plus delta R, well, delta R plus, or delta R cross F is 0. So you're just going to get R2 cross F equals R1 cross F. Okay. Three-dimensional thinking. So here's F, here's R, and here we have the shaded area, this plane here. The moment's going to be perpendicular to this plane formed by R and F. Okay. If some of the moments, just add up all the R cross Fs. We've done that before. I was already using this back in my Excel spreadsheet. Just add up all the moments. The moment caused by this force, and then the moment caused by this force. You just add them all up. About point O. Okay. So let's determine the moment of this force, and I will pick up this problem when we get back.